thank the organizers so to let me give the two presentations on the well, to thank them for organizing this nice meeting. And so this presentation is about Rheophysics of wet granular materials. In fact, I've focused my presentation on this theme. I propose to speak also of the influence of shape of grains, but I have not enough time. And so this is a work done, in fact, by Saïd Ramzeh, a PhD student in Laboratoire Navier, under the direction of Jean de Helroux on the small part of myself. So we are dealing with dense assemblies of spherical grains, frictional spherical grains, which with a certain amount of liquid, which gives rise to liquid bridges. We are considering here small saturation, so that we are in what is called the pendular state. We have the liquid bridges involved only 2 grains. These bridges introduce cohesion force, which is proportional to the surface tension of the liquid onto the contact angle, and proportional to the size of the grains. And this force, the force between the 2 grains, depends. The liquid bridge within the model which we have chosen, the liquid bridge has a constant volume. There is hysteresis, so it forms when particles touch, and there is a rupture of the liquid bridges for a distance larger than d0, which is simply related to the volume of the meniscus. And the dependency of the capillary force as a function of the distance between the grain has been chosen to be described by the so-called Mogis model, while the other contact force, normal or tangential, are described as usual for dry grains. We study homogeneous shear states of such systems, with the usual method controlling normal stress and shear rate. We have frictional grains, number of grains of 4,000, and we are in the rigid contact limits, so a high stiffness number. The rheology of this system will be described by both the inertial number and another dimensionless number, which describes the intensity of cohesion, and this can be called the reduced pressure, so ratio of the typical force acting on the grains due to pressure to the cohesion force. And we want to describe the shear state through the dependency of solid fraction on effective friction as a function of those 2 dimensionless numbers. Just before showing the results, I tell you what is the range of saturation and reduced pressure which we are considering. We have chosen volume of liquid bridges, which is 10⁻³ as a function of the volume of the grain, which means that the rupture distance is 1/10 of the diameter of the grains. The saturation can be shown to be given as this dimensionless volume of the liquid bridge times a coordination number z on the with function of simple function of the solid fraction. So in fact, in our simulation, the saturation is not constant. It depends. It depends on inertial number, on the reduced pressure. But in fact, the results show that the dependency is very small. So essentially, it has no effect. We have to have in mind that the validity of the previous model is correct for a saturation between a lower value, which would be of order 10⁻³ below this value, we have influence of roughness, and above a value of 10⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻⁻ another description, another model has to be used. And the typical values which are studied here are in the range of 10 minus 2. And for the reduced pressure, if we consider a grain of 100 micrometers on the water, a reduced pressure of value of 1 corresponds to a pressure of 10 kilopascal. Well, sorry, 2.5 kilopascals. That is to say, a height of grain of 10 centimeter in the gravity field. So the constitutive laws which have been measured have the following are shown in those graphs. So the usual increase of mu star as a function of I, decrease of phi as a function of I, and the important thing is that you have a strong increase of mu star and strong decrease of phi as when the reduced pressure decreases. And well, so the change is significant, and we must also notice that it is already present for value of the reduced pressure of the order of 1 or even larger. And this is in contrast with what was observed in other simulations. So the one of Rognon a few years ago, and also the one which were shown by Pierre Job yesterday, where well, there is the same tendency, but for much smaller value of reduced pressure. That is to say, much larger cohesion. And so then the question is why? On a possible, well, our explanation is a strong effect of the distant interactions. In the previous analysis, so the model of chosen by Pierre Rognon, the cohesion force was active only for grain at contact. And so here I compare a model for dry grains, no cohesion, with a model in blue with with cohesion of contact. So there is an well, the value of P star is already strong, already small, strong cohesion, 0.4. And so there is already a significant increase of mu star. But when I consider the Mogis model with two different values of the rupture distance, I see that you can see that there is another significant increase of the effective friction. So this tells us that distant interaction plays a significant role. However, if we measure the contribution of those distant interactions to shear stress, which is shown on the left graph, you see that it remains small, less than 10%, and the same for the contribution of capillary force to the shear stress. So why? So let's have a look at the microstructure. So there was a first observation, which was the strong reduction of the solid fraction. So first observation, this reduction is not homogeneous. The fact that the observation related to the coordination number shows us that the material is well, in some way agglomerated in clusters. And another observation is the evolution of the contact duration as a function of the cohesion. So the contact duration is around the shear time for small cohesion, and is increased here by factor 1.7, yes, for strong cohesion. So there is a clustering effect. So the cohesion stabilizes a new structure in which will be responsible for the increase of effective friction. And so the next, in fact, last quantities which I want to show is another description of the microstructure associated to the anisotropy of contact forces, contact network, and contact forces. So here, what is shown is what is called the fabric tensor, and well, I just comment on the fxy component of this tensor, and here what is shown is that there are essentially so those components which are strong, and the stronger one is the one associated to distant interactions on such a value, and this is associated to the receding particles, while the other smaller value is associated to approaching pairs and correspond to contact interactions. So about this question, there is some work in progress. At least, well, a few years ago, Pierre Rognon showed that it was possible to relate the effective friction to the force anisotropy in a two-dimensional system through this formula. So this is a formula associated to the normal forces. Another part would be associated to tangential forces. And so the idea was that when you increase cohesion, you change the in fact the product of the density of contacts by the average force normalized by the force normalized by the average force in the system. And when you increase cohesion, you increase contacts in this direction, and you get a value of zeta n which becomes negative in this other direction. So this is consistent with what is shown here. And so we are trying to make such an analysis, but at this stage, what has been measured is the contribution to the shear stress associated to the normal contact forces, which is the dominant part of the shear stress, as a function of the contact anisotropy on the average force anisotropy. So the difference with the previous formula is that here you can look separately to the two contributions, and this shows that at this stage, so this shows that the dominant part is the anisotropy of the average force. And so I conclude. So by saying that in those systems there is so a large effect of capillary force, even for small value of cohesion. This seems to be due to the influence of distant interactions, which means that it is important to choose a good model for the force model in such system. There is so some indication of a clustering effect, while not really characterized properly at this stage, and there is a strong effect also of contact on force anisotropy. And well, there are still many questions, such as I've not shown the shear localization which occur for large cohesion. The viscous force, which may play a role, have not been included yet. In this model, we do not describe the transfer of liquid between the grains when the liquid bridges breaks, and we might want also to describe larger saturation rates and to make comparison with experiments. So, thank you again.
You have mentioned that one of the perspectives is to make comparison with experiments. Do you know of any works that have been published already, experimental works on this subject?
Well, there are some works, but I'm not sure to really have a work which tells something about the rheology itself, the constitutive law itself. No, I will not be able to. There have been many experimental works on wet grains, but on the rheology, they are not. In my opinion, they are not sufficiently accurate to give an indication on the rheology.
Yes. Which length scale are you using when you calculate your inertial number for working out your friction?
The size of the grain?
So when you've got a cluster that's held together by capillary bridges, wouldn't you expect that the scale of the cluster should be involved in that somehow?
Indirectly, the analysis shows that it's still possible to use the traditional inertial number, even if there might well be some clusters in the system.
Okay, if no more questions, that thanks to speaking. Yep, again.